2211, Lab 3 on black hole. So a preview of the purpose and result of this lab. The purpose of part 1 of this lab is to use a Python simulation of the interaction between a star and black hole to find the mass of the black hole. The purpose of part two of this lab is to use a similar Python simulation with the addition of a third object, a ship, to find the necessary initial velocity of a ship in order for it to exit a planet and the gravity of the black hole and the planet without crashing into either other object. The result was that we found was the mass of the black hole is about 1.063 times 10 to the 34th kilograms, and the required initial velocity for the ship to exit was negative 9.5 times 10 to the 6th in the x direction and 8 times 10 to the 6th in the y direction. Newton's second law. So some models and principles that we'll be using in this lab, 3 things derived from Newton's second law. The momentum principle, which is that F net is equal to the change of momentum over the change in time, or the rate of change of momentum with respect to time. And the velocity update formula and position update formula, as in the other labs we've done. The universal law of gravitation is very important in this lab, which states that the force of gravity is equal to the gravitational constant, 6.67 times 10 to the 11th, times the mass of the two objects over the distance between them squared, times r hat, which is the unit vector in the direction of the force, which points between the two objects. Parallel and perpendicular forces are also important in this lab. Parallel forces are in the p hat direction, which is the direction of the momentum of the object, which this changes the speed of the object, and the perpendicular forces are in the n hat direction, which is perpendicular to the momentum of the object, and these forces will change the direction of the object. So part 1, finding the mass of black hole. The system in this part was the star and the black hole, and the surroundings were just space. The initial conditions used for it were the gravitational constant, obviously, the mass of the star, which was 2 times 10 to the 30th, and the time between our data points, which is 1 day, which is in seconds, 86,400. So the code for part 1, we find that the initial and final momentum of the star, using the definition of momentum and the initial and final velocity, which is mass times velocity. We find the change in velocity and change in momentum just by finding VMP final minus VMP initial, and then we calculate the rate of change of momentum with respect to time by putting delta p change of momentum over delta t change in time. And then we use second law to calculate F net, which is the change in momentum. So dp dt equals F net. All right, then in lines 178 to 183, we find the parallel net force by finding the momentum in the p hat direction, and that's equal to the parallel force, and then using a similar process to find the force in the perpendicular direction, just subtracting what's left of the change of momentum from the parallel piece. Then we calculate the mass of the black hole by using a rearranged gravity equation on line 193 here. So the result of this, we found that the mass of the black hole was equal to about 1.063 times 10 to the 34th kilograms. So what does it mean? This question was, how are the net force and its parallel and perpendicular components different from the rate of change in momentum and its parallel and perpendicular components? In this case, there's not much difference. The F net is actually equal to the rate of change of momentum with respect to time. So if it were with respect to something else, they would be different. In this case, since it's with respect to time, they are the same. And the perpendicular and parallel components will be the same in this case as well. We can find F net using change of momentum, and change of momentum can be found from just observing the surroundings. And possible sources of error include rounding the gravitational constant, and the time interval used in this was rather large. I could also have let the code run for a longer period of time to get a better estimate for the mass of the black hole. So for part 2, finding the initial velocity of a ship. The system was the ship, the surroundings were the black hole, the planet, and space, and the initial conditions included the mass of the black hole from part 1, and the mass of the planet, ship, which were 9 times 10 to the 28th and 7 times 10 to the 10th respectively. Using the position and velocity update formulas, we could calculate the positions of the planet and ship in the top part here, and the gravity equation was used to find the force between the 3 objects, the net force on the ship and the planet. Using guess and check, I was able to find the necessary relationship of the ship speed in the x and y direction, seen here, in order for it to go into an orbit around the black hole and then exit. The what initial velocity would the ship need in order to enter an orbit around the black hole, something similar to the planet, but slightly more so that it wouldn't collide with the planet. So we found that the planet speed +1 was sufficient for it to enter an orbit. Some possible sources of error in part 2 and the what if are that g is rounded and the mass of the black hole is rounded from part 1.